Hi everyone, this is Anushka and welcome back to my channel in Economist. So if you are someone who is following my lecture videos, you will know that we are studying about the panel data, right? Panel data. And in the previous few videos, we have covered in detail the different methods of estimation of panel data. And only one method is left that we will cover in today's video, right? If you haven't watched those videos, please check that out. I have explained what is the fixed effect model estimation and also the different models with different degrees of flexibility, right? So we have done 5 different estimation methods. So before going into this video, it is mandatory for you to go through those lecture first because otherwise you will not understand anything in this video, right? So this is basically a continuation of our previous video where we will go into the final method of estimation of our panel data, which is known as the random effect model, right? Random effect model. So particularly what we will do, we will go into the structure of the model. This is what we always do before starting of our lecture. Then we will go into the different assumptions. What are the different assumptions required for this kind of model? And finally, we will go into the estimation process. Estimation process, what is the method in which you can estimate this kind of model? We will go into all these things in details, right? So please watch the video till the very end. Otherwise, the concept will not be clear to you, right? So let's start with the model today. So here, the model that we will use will be quite similar to the fixed effect model that we have done earlier. So see, what will be the model? Model will be like this. YIT is equals to beta 1I. I hope you have, seen this thing before. Beta 1I plus beta 2 X2IT plus beta 3 X3IT plus UIT. Now we are using the same context that we have used for all our estimation methods, that we have 4 different firms, namely 1, 2, 3, 4, or ABCD, anything you can consider. You can consider it to be 1, 2, 3, 4, 4 different entities or cross-sectional units. In our context, these are 4 different firms, and we are measuring them, measuring the output of each of these firms for 20 different periods. So in our case, T will be 1, 2, 3, 4 up to 20, right? So up till this much, this is fine. Now there is a important distinction. Here, see, this is the model structure that we have used in case of fixed effect also. But what is the distinction? The main difference between this model is that here the intercept term that we are considering is not a constant. It is not a constant. This is a random variable now. This will be a random variable now. And this is the main point of distinction between fixed effect model and random effect model. So let me write it down. We assume, here, we assume that beta 1I, that is the intercept term, is not fixed. This is not fixed. This is a random variable. That is why the name is the random effect model, because we are capturing the entity effects individually, but it will be random in nature. The nature of this estimation will be random. That is why it is a random effect model where this expectation, the expected value of this beta 1I will be beta 1, right? We assume that the expected value of this beta 1I will be beta 1. In our previous case, in our previous cases, that is basically in the fixed effect model. Basically, we have done the fixed effect model. There, can you pause the video and tell me what will be this? In case of fixed effect model, this is a constant. In that case, beta 1I was a constant. So if you take the expectation of a constant, what should we get? We should get the constant itself, right? So it was beta 1I only, which is a constant in case of a fixed effect model. So this is the main point of distinction that we must know. The structure of the model is absolutely the same. See, we have done this similar thing in the fixed effect model also. But the only point of distinction here is that the intercept term, The intercept term, we have again introduced the entity specific heterogeneity through the varying intercepts. But here the only point of distinction is that this intercept is not a constant. Instead, it is a random variable. Which kind of a random variable? Where this expected value of this random variable is simply beta 1. Now we will go into the structure of this beta 1 I. And now the point of distinction has to be remembered that in case of fixed effect model, structure is the same, but the expected value will be simply beta 1 I only. This was a constant. If you take expectation of a constant, then it will be constant only, right? Now let us go into the structure of this beta 1 I. So we can express the intercept value of individual firms. So we are doing everything keeping in mind the context that we started off. That is why I have written here individual firms as what will be the structure of this beta 1 I? This will be simply beta 1 I is beta 1 plus some EI. It will be some EI. EI is nothing but the cross-sectional varieties, basically, cross-sectional heterogeneity. So this beta 1 I will be simply this for all I equals to 1, 2, 3, 4, where this beta 1, it represents a constant that we have seen. This is the constant, means this is the expectation that we have done here. This is the constant, and this is basically the cross-sectional error. This is basically the cross-sectional error or the cross-sectional heterogeneity, or you can write it to be the individuality of each form. Individuality of forms. So this is the general structure of the model. Also, we assume that expected value of EI is 0 for all I. The variance of EI is sigma square for all I, which basically means EI is also a random variable or random error term with the given properties. Right? What are the properties? This is the first property and this is the second property, right? So this is the general structure of this particular model, and this is what is the main point of understanding. So many people I know, many students, many researchers even don't understand what is the difference between the fixed effect model and the random effect model. The main agenda to make this video is to understand, to make you understand this concept, what is the point of distinction. The structure of the model I know is exactly the same. If you write the model in this fashion, it's very difficult to understand what is the distinction, because in fixed effect model also we have done the similar thing. But the point of difference here is the main structure of the intercept. The entity specific variation that we depict through the intercept term, that is completely random. That is completely random. It is composed of two different things. First is a constant term. And the second is an individual specific heterogeneity, or which is known as the cross-sectional heterogeneity or individuality of the terms. So here we can write a note about this. Here we should write, here we assume that the four firms which are included in our sample are drawn from a large population of such firms. So we have randomly chosen four different firms of some features, and they have a common mean value They have a common mean value which is given by beta 1 in our scenario. Remember beta 1. This is the common value that we have. This is a constant value means it represents a common basically production. If you consider the production of the form, it represents that common production. This term is beta 1. So it should have a common mean value beta 1 and the differences in the intercept values of each forms are included in the entity specific error term, with what we named as EI. Right, so we have two different things. One is the constant mean value and another is the entity specific error term, and this is how we have written it. So this beta 1 here, beta 1 is the common mean of the production of four different forms, and this is the entity specific heterogeneity that we have introduced, right? So this is the node that we need to consider. Now, if beta 1i is like this, beta 1i is beta 1 plus ei, then how will you write the original model? If you replace that in the original model, our model will look something like this. YIT, it remains the same. Instead of beta 1i, you will write beta 1 plus beta 2 x2it. This remains the same. Beta 3 x3it. This also remains the same. Now, we will write EI. EI is the term that we have introduced and UI. For all I and T, now this will be the new model that we will consider. Now you can combine these error terms together. Beta 1 plus beta 2 x2it plus beta 3 x3it plus, instead of this EI plus UIT, you can write this to be VIT. This is VIT for all IT, where this VIT is nothing but EI plus UIT is called the composite error, right? Composite error term. This VIT is known as the composite error term, and this term will help us to go into the different estimation method. We will use the generalized least square method. Why do we use that? This will be determined by the nature of this VIT. This we will see later on in our lecture, right? So this is the VIT that we can derive. What we have done, simply instead of beta 1i, we have write beta 1 plus EI, and the rest of the things are remaining the same. As I have told you, this EI is the cross-sectional error term. I am not writing this again. If you are taking notes, you can write this, that EI is the cross-sectional error term and UIT is the idiosyncratic error term, or known as the panel data error. Or let me write it down for your purposes. This is the cross-sectional error. This is the cross-sectional error or the entity-specific error, whatever you want to call it. And this UIT is the idiosyncratic error. Idiosyncratic error, or what you call as the panel error. Panel error, which combines both the cross-sectional and the time series errors. Right? Idiosyncratic error means it consists of both the cross-sectional error terms and the time point error terms. That is why the suffix has I and T both. So this is the usual structure. This is the usual structure of our random effect model. This is the usual structure of our random effect model. Now, there are different assumptions that you have to make for this model to be estimable. Before going to estimation and to have a proper structure of this model, you need different assumptions. And here we will find out, we will write down these assumptions one by one. Let us see what are the different assumptions that we have to make. So important assumptions for random effect model. What could be the possible assumptions? The first assumption is that the EI, the term that we have introduced, it should follow a normal distribution with mean 0 and the variance is sigma E square for all I, right? So it does not have any time influence. It is basically a stationary term which follows normal distribution with mean 0 and the variance is sigma E square. Now the second assumption is that expected value of EI, UIT, that should also be equals to 0. What is this? EI, these two terms we have just introduced. EI is the cross-sectional error and UIT is the idiosyncratic error or the panel error. So panel and the cross-sectional error are completely uncorrelated. Panel and cross-sectional error, panel and cross-sectional error are uncorrelated. So this is the second assumption. Now go to the third assumption. Here we will assume expected value of EI, EJ. This is also 0 for all I and J, right? Expected value of EI, EJ is 0 means the forms are the production of each forms, they are also uncorrelated. Each form's production is also uncorrelated. This is also uncorrelated among themselves, right? So this is the third assumption. Now we will go into the fourth assumption. Let us go to the fourth assumption. The fourth assumption says that UIT, that is the idiosyncratic error term, this will again follow a normal distribution with mean 0 and the variance is sigma U squared for all I and T. So the cross-sectional error term EI, this also follows normal distribution with a constant variance, and UIT, that is the idiosyncratic error or the panel error, this also follows normal distribution with mean 0 and the variance is sigma mu square, which is a constant variance. The fifth assumption is important. It says expected value of UIT, let me write it, UIT, UIS is exactly equals to expected value of UIT, UJT is equals to the expected value of UIT, UJS, which is exactly equals to 0 for all I not equals to J and T not equals to S. So what does this thing mean? This basically implies that the individual error components are not correlated. They are not correlated to each other and are not autocorrelated across the time and individual. So see, what does this particularly mean is that, look at this first term, expectation of UIT, UIS, which basically means is that with respect to the idiosyncratic error, or panel error, the data points or the error terms are completely uncorrelated, right? With respect to time, see here you have T and here you have S. With respect to the time component, the idiosyncratic error means the panel error, they are completely uncorrelated. So let me write in short, with respect to time, the panel error is uncorrelated. This is what I have written in green basically here. Now, what is the second term? Second term is expectation of UIT, UJT. Can you pause the video and think what this means? This basically means each form is uncorrelated among themselves also, right? This is we are talking about the I variables here. Here we are talking about the T variables, and here we are talking about the I and J. See, I and J is varying. So basically, each form is uncorrelated among themselves. So let me write each form is uncorrelated, correlated among themselves, right? And the final term is what? Expectation of UIT and UJS. So here the time and the entity both are varying. See, time and entity both are varying. So with respect to both time and cross-sectional error term, the idiosyncratic errors are uncorrelated with each other with respect to both time and the entities. UITs are uncorrelated. Right? UITs are uncorrelated, and this is what it means. That is by combining all these things, you can write then the individual error components are not correlated with each other and they are not autocorrelated across time and individuals, right? In short, you can write this particular thing, right? So these are the various assumptions that you have to make in order to state this model to be the random effect model. Also, there is another property that you can devise. This is, let me write it in a note, that here the cross sectional error term, which we have denoted to be EI, is not directly observable, is not directly observable. So we only know the properties of EI, that it follows normal distribution, the mean is 0, the variance is sigma e squared. So this much we know, but actually this cross-sectional error term, that is EI, this term is not directly observable. So this error term is called unobservable, or latent variable, latent variable, right? So this is an important point that you have to know if you want to find out what is the variance of VT then, or variance of VIT. That will be simply variance of EI plus UIT, which you can break it down, variance of EI plus variance of UIT. So this will be simply variance of EI is sigma E square, and this will be simply variance of U square. So this is basically a constant term. This is basically a constant term. This is basically the variance of the composite error term that you are having in your random effect model. And this is coming out to be this sigma E square plus sigma U square, which is a constant. Now, if suppose in some case sigma E square becomes 0, suppose if sigma E square becomes 0, then can you tell me what will happen? Can you pause the video and think for a bit? What will you have? If sigma E square is 0, which basically means variance of VIT will come out to be sigma U square only. Variance of V square will be, so variance of UIT will be simply sigma U square. In that case, the random effect model, which is in short written as REM, reduces to the fixed effect model. Fixed effect model. So see that this EI term is extra here. In case of random effect model, this individual specific error term This cross-sectional error term is the extra term here. In fixed effect model, we had this idiosyncratic error term. This was there, but this EI was not there, right? This EI was not there because there the intercept term was itself representing the heterogeneity. So beta 1 I was the varying term there. It was a constant, but for each individual I, that was different. So for the form A, if I is A, then the term will be beta 1A in case of the fixed effect model. If I is B, then it will be beta 1B. Similarly, it will be beta 1C and beta 1D. So this was individually, this is constant, but it will vary across the forms. It will vary across the forms. But here what is happening is that in case of random effect model, if you vary I, what will happen? The intercept, the constant part is there. The constant part is not changing, but the error term is changing. This will be the first thing. Then you have, this is the second thing for the, for when I is C, this will be the third thing, and for D, this will be the thing. So this is the difference. This is how the things are changing between the fixed effect model and random effect model. So this EA term is extra here. This additional error is being introduced in the model in order to capture the individual specific heterogeneity in a more vivid fashion, right? So I hope with this you got the distinction between the fixed effect model and the random effect model, and in which scenario the random effect model will reduce down to the fixed effect model, right? So I hope this much is absolutely clear to you. Now the important question is, how do you estimate this model? How do you estimate this model? Now, for that, one distinction has to be very clearly known, that in fixed effect model, if you remember, when we have studied fixed effect model, I have told you that the individual specific, this unobserved heterogeneity term, right? The unobserved heterogeneity term that we have, you know, introduced in our model, that is correlated. EI was correlated. EI, if it was introduced in the model, it was correlated with the explanatory variables, with X variable. That is, we had the condition like this: covariance of EI XIT will be not equals to 0 in case of fixed effect model. But the random effect model is different. Here we will assume EI is not correlated. Here we assume EI is not correlated with the individual XI variables, which means covariance of EI and XIT will be completely 0 here, right? This is the main point of difference. Although I will make a separate video on this, what is the distinction between fixed effect, random effect in more details. The next video will be devoted to that. Also, we will go into the Houseman test to find out which model will be better in which scenario. That we will do in the next video. But as of now, just for your concept, please remember, this is the main distinction. Now the question is, how do you estimate this model? How do you estimate the random effect model? To estimate random effect model, firstly, we need to check the property of the composite error term. So initially, I have told you the property, one of the properties of VIT will help you to understand where is the problem. So firstly, let us find out what will be the covariance between VIT and VIS. What will be the covariance? So covariance will be VIT is simply EI plus UIT, and VIS will be EI plus UIS. So if you find out the covariance, it will be EI plus covariance of EI UIS plus covariance of EI UIS plus covariance of UIT UIS, right? Now, can you individually say what will be this? What will be this? This will be simply, let me take another color. Yeah. So this thing will be simply variance of EI. Now, what will be this? This is by our assumption, this will be 0. Let me go back to the assumption that we have done. See, UIT. So UIT, EI, this is uncorrelated with each other. So by that logic, this term will be 0. Similarly, this term will also be 0. And similarly, this term will also be 0. So this idiosyncratic error term are IID. They are individually, independently and individually distributed with mean 0 and variance sigma u square. So this is also 0. The cross-sectional error term, the error terms are serially uncorrelated basically. So this will be only sigma e square. So this is the covariance. This is the covariance. Now, using this, you can find out what will be the correlation. Correlation between VIT and VIS if you find out. So in the numerator, you will have this covariance. VIS upon root over of variance of VIT into root over of variance of VIS. This is what you will get. Now the numerator, this is what we just found out. This is sigma e square. This is sigma e square. Now in the denominator, what you will get? You will get sigma e square plus sigma u square into the same thing. Into the same thing. So altogether, this will come out to be, this correlation will come out to be sigma e square plus sigma u square. So this is what is the correlation between VIT and VIS. So what you can say from here, what you can say, we can say that the composite error terms are correlated. So this thing is strictly greater than 0 because all the variances are positive. All the variances are positive. So in other words, this is basically not equals to 0. This much we can say. This is strictly greater than 0, which is not equals to 0, which basically implies that the composite error terms are correlated. Now, if the composite error terms are serially correlated, then we cannot use the usual methods of estimation. The usual methods, so you cannot, use the pooled OLS here or any other estimation method you cannot do. So you have to use some transformations. Basically, let me write. So the composite error term, VIT is serially correlated. This is serially correlated. Moreover, the correlation is positive. The correlation is positive, right? Correlation is positive. Due to this reason, the pooled OLS, standard error, will be incorrectly estimated, or let me write, it will be incorrect. Either it will be very high, or it will be very low. So either it will be overestimated or it will be underestimated, and as a result, our t statistic will be incorrect. This will also be incorrect because remember in the t, what we do, beta cap upon the standard error of beta cap. This is the general structure. So if the standard error is not correctly estimated, then the t statistic will also not be correctly estimated. And if this is the scenario, then all the subsequent analysis, that is inferential analysis, hypothesis testing, confidence interval estimation, everything will be wrong. So if this correlation is present, see, that is why we have found out this correlation. If this correlation is not equals to 0, here it is strictly greater than 0 because it is the ratio of variances. Basically, variance can never be negative. Since it is strictly positive, that is what I have written. Composite error term, that is VIT, is serially correlated, and this correlation is strictly positive. If this is the scenario, the pooled OLS standard error will be incorrect. So you cannot use the pooled OLS method of estimation in this case. So what you have to do, instead you have to use the generalized least square method. In order to estimate using random error model, you have to use something called the generalized least square method. So in this case, we use the generalized Generalized least square method. Generalized least square, which is also known as GLS method, to solve this autocorrelation problem. To solve this autocorrelation problem. So how do you do that? For that, firstly, remember one thing, that the GLS method is especially helpful. This GLS method is especially helpful for the balanced panel. Remember, I have given you the distinction between the balanced and the unbalanced panel. Usually, GLS is applied when we have the balanced panel, where we have cross-sectional units, usually helpful when n goes to infinity and t is relatively small. T is relatively going to zero, basically. So GLS as a method is especially helpful when we are working with a balanced panel, when these cross-sectional units are very high, infinitely many cross-sectional units, large number of cross-sectional units are there, and lower number of time points are there. That is, T is relatively small, but the cross-sectional units are very large. In that case, this GLS method is very useful. But suppose you don't have the balanced panel, which usually you don't have. In our real life scenarios, there will be many missing data that you have to, approximate and impute in some other way. So in general, we can also extend this method. We can also extend the GLS method in case of unbalanced panel. Unbalanced panel. So for that, what you have to do? So for that, we define a proper fraction. What we do? So remember, in case of fixed effect model, what we have done in order to transform the model, what we have done, we have used the time demeaned variables. Remember, we have taken the average over all the time points, and then we have found out what was the time demeaned variable of y, what was the time demeaned data on x, what was the time demeaned error terms. So we have used that method, right? Time demeaned data, and then we have got the transform model and then I have said that we have to use the pooled OLS method. And here, the method is a little different, where what we do, we have to define a proper fraction here. We will define a fraction. The fraction is like this, theta. Suppose theta is a fraction that we define, which looks like this, sigma u square upon sigma u square plus sigma of some alpha square. So sigma alpha is basically a constant, sigma alpha. So instead of alpha, we can write it to be beta as well. We can write it to be the beta as well. The common mean, basically the intercept term that we have used. So some fraction, basically some fraction that we have to consider. This alpha, beta, they are some basically variables, right? So we have to define, before going into the model, to transform the model, we have to define a proper fraction which looks something like this, where this theta should be lying between 0 and 1. Now, if you have this, how do you write the model? Then the transformed equation will be given as this. Firstly, write the model that you have. YIT is beta 1 plus x2 it plus, sorry, beta 2 x2 it plus, let me write it, beta 2 x2 it plus beta 3 x3 it plus vit. This was the model that we had. Now what you have to do, you have to simply firstly, we will take the mean of this. So it will be beta 1 plus beta 2 x2 bar plus beta 3 x3 bar plus vi bar. And then what you have to do, multiply by this theta on both sides. So theta yi bar equals to, this will be theta into the entire thing, beta 1 plus beta 2 x2 bar plus beta 3 x3 bar plus vi bar. Now, if you have a model like this, then we will subtract. So this will be yit. So what we are doing, this is number 1 and this is number 2. Then we are subtracting. So yit minus theta yi bar. This will be the left hand side. And on the right hand side, what we will get? So beta 1 we will take out. Beta 1, if you take out, it will be 1 minus theta, right? See, here you have beta 1, here you have theta beta 1. So beta 1 minus theta beta 1. Beta 1 minus theta beta 1 can be written as this. And then what you do? You take the beta 2 out. Beta 2, if you take out, what you will have? x2it. And then you have theta x2 bar. Theta x2 bar plus take beta 3 out. Theta x3 bar. See, take this beta 3. So if you subtract, beta 3 will be x3it minus theta x minus beta theta x3 bar, and plus this term remains the same, vit minus you have what? Theta vi bar. Theta vi bar, and this will be the transformed model. This will be the transformed model that we have to ultimately use. Now from here, what we can do? This is our transformed model. It can be shown in that case. It can be proved. It can be proved that the composite error terms, that is this composite error term now will be uncorrelated. This will be uncorrelated. That is covariance of VIT, VIS will now come out to be 0 in this transformed model where T is not equals to S. Right? So this is the new model now. Now it becomes a model that is estimable. Now you can use the pooled OLS method and then again try to estimate the parameters of this model, right? So in the fixed effect model, what we have done, we have only taken the difference. Firstly, we have taken the average over time in both sides, and then we have taken the difference. That was the fixed effect model. But in case of random effect model, what we have to do, we have to appropriately set one proportion. We have to appropriately set one proportion, a fraction which should lie between 0 and 1. Here I have taken this specific case. This is the fraction that I have considered, and then we have to first multiply it. We have to first multiply it, which we have done here. Firstly multiply and then take the difference. Firstly multiply and then take the difference. The model that you will get will be the transformed model. And now this transformed model, the composite error term that you will get from this transformed model, that will be uncorrelated with each other. So basically, why we have to do all these things? Because see, this is the reason. We have found that the composite error terms are correlated. If you use the original model, original random effect model, if you use, then you will see the composite error term will become correlated, and this correlation cannot be present. If you use the pooled OLS method, using this correlated data, serially correlated composite error term, then it will be not correctly estimable because it will either inflate the standard error or it will deflate the standard error. This is what I have written here. That is why you have to transform the model using the generalized least square method. Then what you have to do? Firstly, set a proper fraction and then transform the model. Now, in this transformed model, you can use the pooled OLS method or any other method because now it becomes uncorrelated, which satisfies the properties of general regression, right? So this is the entire thing that I wanted to share with you. This is all about the random effect model. If you have any questions anywhere, please let me know. Let me quickly show you what we have done in today's class and then I'll stop. So firstly, we have started off with a model and I have told you what is the main point of difference between the random effect and the fixed effect model. The main point of difference is that the intercept term is now a random variable, which is composed of two different components. First is the constant beta 1. Beta 1 is a constant, which is the common mean term. And then you have individual specific heterogeneity, which is given by EI, which is also known as the cross-sectional error term. And we have assumed many different things. What are the different things that we have assumed? Okay, so firstly, we have, rewritten the model as this, incorporating the properties of the intercept term. Then we have gone into different assumptions. We have, assumed the distribution of EI. We have said that the panel and the cross-sectional error terms are uncorrelated. Also, each firm's production is also uncorrelated among themselves. UIT, that is the idiosyncratic error term, also follows normal distribution, and also the individual components are not correlated, or no autocorrelation problem is there across time and individuals. Now, if you have that, you can find out the properties of this composite error term that we have defined. And we have said that if the sigma E squared is 0, then the random effect model boils down to the fixed effect model. Right? And then we tried to estimate using this model. The main problem that we faced is that the correlation, we have found that the composite terms are serially correlated with each other, and that is true positive serial correlation. Positive correlation is there. If that is the case, pooled OLS method will fail because it will inflate or deflate the standard error. So in order to solve this problem and in order to make the composite error term uncorrelated again, what we have done, we have used a transformation. We have taken into account appropriate fraction and then we have multiplied it. We have multiplied it with the model itself and then we have taken the difference which has given us this transformed model or the transformed equation. Now this equation is completely estimable because here no problem of serial correlation is there. You are transforming the model just to eliminate the problem of serial correlation, and that is how you have to do it theoretically, right? So in Stata, R, and Python, you have different softwares to use this to implement this thing. I'll make a separate playlist on that. I have not included them because I don't want to make this video any longer. If you want, you can do this for yourself also. You can use this softwares to execute in your own case. And if you have any questions, any doubts anywhere, please let me know. In the next video, we will go into the difference between the fixed effect, random effect model in more details, and then we will go into the Hausman test, which will help us to statistically decide that which model is more effective in which scenario, right? So we'll do statistical testing to find out in which scenario, fixed effect model is more useful, in which scenario random effect model is more useful. We will go into that, right? So as of now, thank you so much for your time. If you like this video, please hit the like button and do subscribe to this channel, AN Economist. If you feel that these videos are helping you to, upgrade your marks and to get this concept in a better fashion, in a clear fashion, then please support my endeavor. I try to post 3 to 4 lecture videos every single week, which takes a lot of time and effort from my end. So if you really like my content and you want me to continue making such useful contents for you, then please support my endeavor and show your love, right? Thank you so much for your time and let's meet you in the next video.